So the topic for this session is 5G new radio synchronization signal. So how synchronization signal looks like in case of 5G, we will look at that. We'll be covering various subtopics like synchronization signal block, that is primary synchronization signal PSS and secondary synchronization signal SSS. Then we'll look at 5G new radio physical cell ID, how PCI is calculated using PSS and SSS. And then we'll look at that in case of this synchronization signal, we call it SSB, synchronization signal block, how we can locate this in frequency domain and also in time domain. So we'll try to locate that, how a user equipment is able to locate SSB, synchronization signal block, in time domain and frequency domain, the concept of SSB bus set, and finally, very brief, we'll look at the procedure, synchronization procedure itself. So let us try to complete this sixth topic in this session. So first, let us look at the SS block, synchronization signal block. There we'll discuss about PSS and SSS, primary synchronization signal and secondary synchronization signal. Okay, so let us look at synchronization signal in terms of frequency, how much frequency or subcarriers or resource blocks are required. So just look at this picture, I think it is pretty clear. So here, if you see this axis, this is your in terms of frequency, so it is 240 number of subcarriers. So in terms of frequency, it is 240 number of subcarriers. If you calculate in terms of RB by dividing by 12, you'll get 20 PRB. So our SS block requires 20 physical resource block, that is 240 subcarriers in terms of frequency. Now in terms of time, this is represented on this axis. We require 4 OFDM symbols. So this is one symbol, second, third and fourth. So there are 4 OFDM symbols which is required for this synchronization signal block. So within this, if you look at your primary synchronization signal is here, PSS. It is in 127 subcarriers out of the 240. This is the 127 subcarriers. The secondary synchronization signal is also in the same 127 subcarriers but in different symbols. So this is one symbol, this is the other symbol. In rest of the location, if you see in this symbol, the entire number of subcarriers in these symbols are for physical broadcast channel, PBCH we call it. In this symbol also, the entire 240 subcarriers are will be having PBCH, and PBCH will also be there in this symbol where we have SSS, 48 subcarriers here and 48 subcarriers here, and rest of the symbols are kept blank in the design. The rest of the subcarriers in these symbols, like the gray one which you see, are kind of blank. So this is kind of a how much number of subcarriers and how many OFDM symbols will be required for synchronization signal block. So now let us look at the primary synchronization signal, PSS. So for what purpose these synchronization signals are used? Basically, we are talking about when you switch on your mobile, right, for the first time, it do not know about the network, which frequency band it is operating, what is the timing and all. So basically the synchronization signal helps those your devices, user equipment to actually synchronize in downlink direction. Please note this synchronization is in downlink direction, right? Because it is receiving the signal. So the SS block is for downlink frame synchronization, right? And in particular, if you talk about PSS, what it gives is first symbol in the radio frame. So basically it will now if my device is able to receive the synchronization signal block, in fact it will be able to synchronize with first symbol in a radio frame. Radio frame is of 10 millisecond. So the first symbol which is coming in that frame, the PSS will give that information, right? So in terms of time, your device will be able to time synchronize with the first symbol in a radio frame. So we have already talked about that this PSS is in 127 subcarriers, and it also provides a value called N2. It also provides a value called N2, which will be used for calculating physical cell ID. We will do that in subsequent slides. So this is PSS. Yes, so if you are able to decode PSS, you are able to decode two things. One is the first symbol in a radio frame, and second is the N2 value. So these two things are present as part of the PSS itself. Is it okay? Now let us look at the secondary synchronization signal. So again, as I said that SS block completely, PSS and BSS combinedly, is for downlink frame synchronization. And what SSS gives is the first symbol in a subframe. So out of the 10 millisecond, the subframe is 1 millisecond. So what is the first symbol when it is starting? So that position is obtained from the SSS. So when our device is able to decode SSS, we are completely synchronized in time domain kind of, because now we also know the first symbol in a subframe. So in time wise, your device is synchronized, right? And it is also there in the 127 subcarriers, and it also provides a value called N1. Please remember N1. So this N1 value will also be used for calculating physical cell ID, N1 and N2. N1, just remember, N1 we are getting in SSS and N2 we are getting in PSS. Yeah, right. So you are right. So it is, the difference is in these two. One is that you are getting position of first symbol in a subframe, where in PSS you are getting first symbol in a frame. And there you are getting N2, here we are getting N1 value. Okay, so now let us calculate the physical cell ID using N1 and N2 value. So how it is? So with this picture, you'll be able to understand. So basically, the PSS gives you N1 or N2, N2 value. So your N2 value can be 0, 1 or 2. Only three values are there in the N2. But with SSS, you get N1 and your value is from 0 to 335. That means 336 number of value. How do you calculate physical cell ID? You calculate it by, you have to multiply your N1 into 3 and you have to add N2. So this is how you calculate, your device will calculate physical cell ID, and it will know that in which cell ID it is. So it will be used in subsequent signaling, the cell IDs and all. So let's take an example. If n1 is say 303 and n2 is say 1, then you can calculate the cell ID 3 into 303 plus 1. So you'll get 910. So your PCI value is 910. So depending upon what N1 or what N2 you are getting, you will be able to calculate the physical layer cell ID or PCI. So yeah, it's similar to LT, right? And so here the value are going up to 1008. So total number of PCI possible would be 1008. From 0 to 1008, that means 1009 values are there. Okay. So now most important part is that what is the location of synchronization signal in frequency domain? This 3 how much it will be? 1 plus 1 maximum value 2 you have to add. Okay. So you are able to calculate 1007. Yeah. That will come. So that means this goes up to 336 maybe here. Not there may be some mistake in this particular number, so it goes up to 1008. I can clarify later on by seeing the document, right? Yeah. So I do not know the region. These numbers are given the specification directly. So I'm just kind of telling you that. So I'm not really aware about the limitation. Okay. Okay. Yeah. Yeah. So that's what I'm saying. There's some mistake in this particular picture. Maybe you are right that it is up to 1008 values are there perhaps. So this in this picture this 1008 written is maybe wrong. It may be a 1007, which I can confirm looking into the specification document later on. ठीक है. Okay, so now the most important question is that what is the location of SSB in frequency domain? So basically your device when it is switching on, it do not know that at what frequency the tower is transmitting, right? So how to search? So any of you, are you aware that in 4G, 3G, 2G, how this search mechanism works? Right. MIB is not available while you switch on your mobile for the first time. No information is available, right? Yeah. So you're right to some extent that in the previous technologies, so there was kind of channel raster that every 5 kilohertz the device look for the signal and it will just keep on searching and it search within the band which it is capable of doing, right? Suppose your device is capable of X and Y band, so the search of that device will be limited to that band. Network may be supporting higher, so it'll start, and those channel raster are standard and device knows that, right? But in 5G, since the support is of very bigger channel bandwidth and frequency bands in low band, mid band, even in millimeter, if it starts searching with 5 kilohertz, 10 kilohertz or 100 kilohertz steps. It will take very long time to complete the entire search of a channel bandwidth of 400 megahertz. So they have, in 5G for the first time, they have come out with a concept of global synchronization channel number. So basically, for the purpose of synchronizations, they have defined a bigger step size for device to look at for the synchronization signal. We call it GSCN, right? And they have given a number also. So we'll look at that, how that location of SSB in frequency domain will be. Okay. So as I was explaining, the synchronization raster is nothing but the frequency position of synchronization block that can be used by UE for system acquisition. So that means you cannot put SS block anywhere. Those positions are already defined, right? So your device will look at those positions only. Suppose my device support only 50 megahertz bandwidth in a certain band. So I would, so for every band, you will have those positions of the frequency where the device has to look for synchronization signal. So it will kind of move from one to the next, to the next, to the next, and it will find wherever it finds, it will be able to synchronize in terms of frequency and decode this synchronization signal. So for all frequency band, this channel number, the GSCN, global synchronization channel number, is defined. So that means you can calculate those synchronization raster corresponding to each number, right? So those are already defined. So your device will know in advance the channel raster or GSCN number for the band it is supporting. It is already programmed kind of in your devices. And those, the frequency which is correspond to a GSCN number is called SSREF. Is called SSREF. Okay. Now the next important aspect is that these SS signal, which subcarrier spacing they will be using, because your device do not know. So the subcarrier spacing is also predefined for SS block for each frequency band separately in the specification, and it is already known by your device, right? So synchronization raster subcarrier spacing used is defined for each band. So there are tables given the specification where what will be the subcarrier spacing of this particular SS block and what will be the channel raster for each band. Those are defined. We'll look at some of it in subsequent slides. So that is, so this table is again taken from the specification document which I have shared with you. This gives you the SSREF, that means channel raster start point frequency, right? And you also have the GSCN number, global synchronization channel number. So, and in the first column, these are the range of frequency from 0 to 3 gigahertz. This is 3000 megahertz. So up to 3 gigahertz, this row gives you what will be the reference frequency of those synchronization signals and what could be their corresponding channel number, GSCN number. So here the formula given is N into 1200 kilohertz plus M into 50 kilohertz, and they have already defined N can vary from 1 to 2499, M will vary, will be either 1, 3 or 5, and with this you can calculate this M and N is for calculating GSCN. So this is the formula given in the specification document. If you go to the higher frequency bands from 3 gigahertz to 24.2 gigahertz, it becomes fairly simple. So here, starting from 3 gigahertz, they are just adding 1.44 megahertz in each step, and that becomes your reference frequency. And your channel number is also sequential, starting from 7499 up to 22255. So it is straightforward. The complexity is there in the lower band only. And again, if you go beyond to 24 gigahertz to 100 gigahertz, here step size is 17.28 megahertz. So that every 17.28 megahertz, starting from 24.25 gigahertz, you will have these SSREF frequencies, and those corresponding number will be starting from here and will end up to this. So just see that step size. So when we say up to 3 gigahertz, those are 900 megahertz band, 1800 megahertz band and all, where channel bandwidth is less. So our step size is less in this case. We will see the calculation. Here the step size, mid band, and of course it is going up to 24.25 gigahertz. Step size is 1.44 megahertz, but in millimeter wave, beyond 24.25, it is 17 megahertz. So why step size is higher? Because otherwise devices will take much longer time to synchronize. So higher the band, higher the step size they have designed. And it goes up to 26639 in terms of channel number, global synchronization channel number. So let me first show you the calculation for this, and then I'll come back to this particular. So just see this picture. So this we have taken for 3 gigahertz to 24.52 gigahertz, how those SSREF frequency can be calculated. So if you look at the table given in the specification, so the GSCN number is 7499 plus N, and N is 01234. So it will start from 7499, right? So your channel number or global synchronization channel number is, say, starting at 7499, and if you have to calculate SSREF, not SREF, SSREF, then you have to do this 3 gigahertz plus N into, this is multiplication, not at the rate, N into 1.44 megahertz. So the first SSREF is 3 gigahertz. Second is uh, this 3001, right, megahertz, 0.144 megahertz. So they have just added 1.44 megahertz. Again add 1.44 megahertz, and you get this specific frequency where possible SS block can be placed, and so on. So the calculation goes very long, up to 22255. So I have just showing few ones so that you are aware of. So here every 1 point, yeah, please. Yeah. So GSCN is a number. So every this particular SREF is also denoted by a number called global synchronization channel number. So many a times uh, the system will know only the channel number, say 7507. So corresponding to 7507, the exact frequency will be 3011.52 megahertz. So that is the only. So just like I mean channel numbers, you define certain numbers corresponding to each frequency. So this is just a number which is defined. Yeah. So basically UV knows. Suppose it supports a band, a particular band. So it knows that what is the GSCN number, because in many of other signaling, even only the GSCN number will be available to your UE at that point of time, right? I'll tell you one example. When NSA mode is working, right? NSA mode, that means you have a 4G core and all, right? And only the radio is of 5G. In that case, all this synchronization happens only for the 4G base stations. All those initial access is through the 4G. Once it is latched to the 4G base station, and 4G base station knows that this device is capable of doing 5G, and there is a NR base station available, so that 4G base station knows the synchronization frequencies. So it will just communicate the GSCN number, right, to the device, and device will be able to calculate the exact frequency and latch into the 5G base station and all, right? So so GSCN numbers are used during the communication for various purposes. So I hope it is clear to some extent. No, no, no. The UE has idea of GSCN, because why I'm saying it is aware of, because UE supports a particular band, and for every band GSCN is already defined, and it is available in the device, configured in the device. So although GSCN and even corresponding SREF, the device is able to calculate within that. Yeah, yes. So it has to start at some point, no? So it is, so the corresponding to that band, it will start at a certain point. So so it knows the GSCN, and it will be able to calculate the starting point. Let's do one example for you. Suppose it is band N2, right? So suppose it is band N2. So in band N2, if you look at the frequencies, it is from 1930 to 1990. That means total 60 megahertz of the band, right? So the GSCN number for band N2 is is already defined in the specification. It will be configured in the devices, right? So it is 4829 to 4969. Okay. So now if you look at the formula for this N2 band, it is less than 3 gigahertz. This formula was there, right? Where GSCN is defined as this. So using this formula, just see this table. If you calculate the value of N, so I have just reversed that formula. GSCN is this. So what will be the N? So N is 1610, right? The first value is 1610, corresponding to GSCN this, and M can be 1, 3 and 5, right? So SREF, if you calculate, it comes to this particular value. So your device knows the GSCN number, and it will be able to calculate the SREF in sequence. Right here, the step size is 100 kilohertz and also 1000 kilohertz. In case this value becomes 5, just see the step size 100, 100,000. So it is not smooth kind of in the first example. Second example of 1.44 was simpler. I hope I'm able to make you clear. Or I'll share you the document and you just go through. Yeah, okay. Okay, fine. So if you now look at the frequencies which are 24.52 gigahertz to 100 gigahertz. So here the step size is 17.28 megahertz. So uh, the device can look at this particular frequency depending upon which band it is supporting, and on that band itself it will look at. So what is the difference? Yeah, please. Haji, Haji. Yes, yes, yes. Why not? Very right. Yes, yes. So basically, in the previous slide, I said that for every frequency band, the subcarrier spacing of SS block is fixed in the specification. So your device knows that in advance. Suppose my device support N71 band. So for that, the subcarrier spacing of SS block is already configured. So your infrastructure base station also knows and your device also knows. So those are already fixed in advance because at that point of time, nothing can be communicated. So it has to be prefixed. Okay, so that's what I will just answer after this slide. So if you compare this with LTE, so in case of LTE, your synchronization signal is always at center of the frequency, right? The synchronization signal in case of LTE is at center. So that's why your device would look at center of the frequency. But in case of 5G, because of concept of BWP, suppose a device supports 400 megahertz bandwidth, but it may be operating on a lower bandwidth part, BWP. For that, the SSB can start from any other frequency position in any of those uh, kind of SREF frequency point or channel raster, we say it, right? So is that answered? Though that means your device has to start looking at synchronization signal in its supported bandwidth part from start of that. Is that okay? Okay. Which one? Which slide? Okay. One. This. Yeah. So generally, if you see the default, just see the node part. The default value for operating band, which only support subcarrier spacing spaced channel raster, is M is equal to 3. So M is equal to 3 would be the default value, but there are cases where it will be M is equal to 1 or M is equal to 5 also. So it will be already known to the devices. The default would be 3. Yeah, yeah. So that particular 240 will be only for synchronization signal block. So that you are absolutely right that for when I said signaling, it was synchronization signal only. Right. Okay. Okay. So now let us look at SSB in time domain. So frequency domain, as we now know that there is a concept of global synchronization channel number, which correspond to specific SRF frequencies, where your SSB can be located in frequency domain. But what what is in time domain? Which so we know that the four symbols are required, but those four symbols are which four symbols out of all the symbols that may be present, right? So let us look at that. So this is again a table taken from a specification document. Uh, so this table gives you that where your SS block can be located in terms of which symbol, right? Depending upon the numerology used, right, of the subcarrier spacing. So just look at this picture. We'll take one example. So let us look at 15 kilohertz subcarrier spacing and this particular row, which is for frequencies which are less than 3 gigahertz. So the positions are symbol 2, symbol 8, right? And then plus 14 into n, and n can be 0. So if it is 0, that means this value becomes 0. So it is symbol position 2 and symbol position 8. So I'll just show you picture in the next slide and come back. So just see what we saw in 15 kilohertz, my two SS block, one starting at symbol 2, other starting at symbol 8. If you just count, it will be, this one will be the 8th symbol, this is the second one. And as we know, one SS block requires 4 symbols, so these are 4 symbols, these are 4 symbols. Let's go back to the table. Suppose my value is 1, then symbol 2, 8 plus 14, right? So if you do a plus 14 into 2, it will be the 16 symbol. And if you do plus 8 plus 14, it will be 22 symbol, right? Symbol number 22, right? So that means, so here, this is 1 millisecond. You have 2 SS blocks. Now in the next 1 millisecond, again, at same position, we calculated, 16 will come here and 22 will come here. The SS block will be there. So that means in this case, the maximum number of possible SS blocks would be 4. So just see the below table, that for frequencies less than 3 gigahertz, maximum number of SS block possible is 4. We will come to SS bus set in the subsequent slide. Similarly, if you look at frequencies which are more than 3 gigahertz, for the same 15 kilohertz subcarrier spacing, here you have n value is equal to 0, 1, 2, 3. So that means its formula is same, but the 2 more values are increasing. That means here we had 4 number of SS blocks. Here we'll have 8 because this 2 and 8 will repeat after 14 number of symbols 4 times. So for frequencies which are 3 to 6 gigahertz, maximum number of SS block possible would be 8. So and then similarly for 30 gigahertz frequency band, if it is being used for less than 3 gigahertz, then I have how many? I have 1, 2, 3, 4 number of SS block. So again true, less than 3 gigahertz, I have 4 number of SS blocks. And how it will look in the picture, just see that one SS block, second SS block, third and fourth. So you can visually also see. And for millimeter wave, up to 64 synchronization signal block would be possible. So can some of you tell me that why we have a large number in case of millimeter wave? Large number of synchronization signal block we have in case we have millimeter wave. Is there any reason for that? Can somebody guess? Yeah, the carrier size is large. You are right. Anything else? Yes, faster synchronization. Any more answers? So if you recall, we talked, I mean, you may be aware about beam forming concept, which we also discussed earlier. So there'll be a beam being formed in different directions, and normally beam forming concept will be used in higher frequencies. Millimeter, definitely it will be used. So there'll be a beam in multiple direction, and every direction you will be transmitting a SS block, right? So the possible number of beam would be 64. So every beam you will be transmitting one SS block. So that's why 64. So you'll be having large number of beams supported. So 64 beams. So this also tells you that uh, in this specification, total number of beams supported is also kind of 64. Theoretically, at least it will be lesser than that, but 64 up to 64 is possible in this particular specification. Okay. So similarly, the placement in various symbols, how it will be for every frequency band, the table is kind of translated and shown here. So I'll not go into detail because the way I explained, I think you'll be able to understand how those SS block would be located on which OFDM symbol in which different case, that is a frequency band and subcarrier spacing. Okay, so I'll just scroll through. So now let us look at the concept of uh, SS burst set. This is a very popular picture. So we talked about SSB synchronized. So that is also written as SB, having 4 symbols because we are showing time in this particular direction. So it is 4 symbols. So SB1, SB2 up to SBL, right? So within 5 millisecond, 5 millisecond means half of the frame or 5 subframe. You transmit a set of number of SSB. And what is the maximum possible? Maximum possible is 4 in case of frequencies less than 3 gigahertz, 8 in case of frequencies between 3 to 6, and 64 in case of millimeter wave. So within 5 millisecond, a number of SSBs would be transmitted. So let us look at if this is an example of beam forming. So in this beam, say SSB1 is getting transmitted. Then the next beam will be formed and SB2 will be transmitted, SB3 and so on. So every beam is having a synchronization signal block, a special kind of a specific synchronization signal block for every beam. So suppose your devices are here. So it will receive signals from various beam, but it will choose, suppose in this example, it will not choose this beam because receive quality may not be good. In this case, the beams are aligned. So maybe it will choose this beam, right? So the second beam, and then it will receive this PSS, SS, PBCS present in the SB and then do the further action. So this is the concept of SS burst set. So within 5 milliseconds, whatever number of SS blocks are transmitted, they are called one SS burst set. And what is the periodicity? So after 20 milliseconds, starting from here, after 20 milliseconds, again this SB will be transmitted. So it's the default value is 20 millisecond. However, it can be changed once the device is on and network is talking to each other. This can be changed mutually, but initially it will be 20 milliseconds. So every 20 millisecond this SS burst would be transmitted. Why I said default? Because maybe for in case of IoT and all, this periodicity would increase. Initially it will be 20 millisecond, but once the devices are kind of latched, it may be mutually decided to be smaller to avoid use of energy, right? So any question on this slide before I proceed? Yeah. Yeah, after 20 millisecond, right, it will repeat. So suppose this device, one device is located at a particular position. So suppose it has received one SSB. So the next SSB it will receive after 20 millisecond in that sense. If you got my point, as we are transmitting every SB on a different beam, right? So suppose there are L, so L number of beams are there. So after 20 millisecond, the SB1 will be transmitted again. So if my device is here, I'll get the synchronization signal every 20 millisecond. Good. Okay, let's proceed. So I'll just walk through this, the process, we call it synchronization process, how synchronization takes place. Although there are many other aspects of it, so I'll just walk through you in a very, very brief, right? So that you understand that once your device is able to receive the synchronization signal, what next? So just look at this picture. So initially, your G node B is transmitting SS bursts in the periodicity we discussed, right? So we also call it beam sweep. And the UV is receiving this signal from various beams, but it decides which beam is best and then it receives that, right? So basically, once it is able to receive the SS burst, so it will decode the PSS. The first thing which it does is decodes the PSS, primary synchronization signal. So basically, uh, it is a known sequence. The PSS is a known set of sequence. So your device is already having those sequences. It will just compare the received sequence and the sequence which it has, right? And it will compare. And once it knows that which sequence it is, it will be able to determine uh, the N2 value for calculating the cell ID. The next thing, after PSS decode, it will decode the SSS from the same SS burst, right? And it will be able to calculate N1 value because there will be so many sequences. We talked about 0, 2, 3, 3, 5. So there will be so many sequences and it will compare and it will match with 1 and it will know the N1 value. Then it will calculate the cell ID. We did that. After that, from the PBCH in the SS block, we also saw that there is some physical broadcast channel. It will be able to decode PBCH and it will also be able to decode the DMRS, demodulation reference signal, and also the master information block. So we have not gone through MIB, SIB concept, but just understand that it is getting all the required information to latch on to the network, right? Within that synchronization signal block, right? So, it gets a certain information and now it will be able to kind of, so it's a kind of, it has synchronized in downlink direction in terms of frequency, in terms of time. So it will now access the G node B, right? So they call it message 1, right? We also call it random access. and then G node B will respond with message 2, uh, and then it will send a RRC connection, radio resource uh, connection, and connection would be set up. So at this point of time, a connection is established between UE and G node B. So that means your UE has synchronized, and now it can transmit data or receive data. So this is what is your synchronization procedure in nutshell. I'll be sharing with all of you that what MIB contains, the detail of that in a document which you can just go through. It's being very complex. I'm not explaining in the session, but you can go through if you are interested in knowing what those contains. Various sub steps you can go through that. So with this, the second session is over. So here also I would like to break and also would request all of you to attempt the quiz uh, related to this. I think quiz 4 I have shared. So may I request uh, Bimla ji to kindly share the quiz for 10 minutes, and then we will start the next session, which is 5G. Yeah, 4. Fifth is after the next session. So fourth, you can also read this QR code and attempt the quiz if it works for you. And Bimla ji has already shared in the chat box. So please attempt it for say. So we will start the next session at 12:10, right? 12:10 we will be starting. So you have about 15 minutes time. So attempt and take break. So 12:10 will be starting the next session.